Okay, the next thing that we're going to be talking about after we've compounded a certain number of times a year, like we did last time, we're going to be compounding it continuously. So it's a great thing when you're earning it, because you're constantly getting the principal added to. We keep adding it over and over. It's constantly earning the interest. So interestingly enough, the formula that we have, the 1 plus or minus r over n to the nt, well, this gets closer and closer to this e value. And not that you really care or want to know, but it gets really, it keeps converging towards this e, and e is 2.718, etc. So when we do this, this is what we call the PERT formula, because hopefully it's fairly obvious. It spells out PERT. P is your principal, E is E, that number in your calculator, and R is your rate, and when it's a decimal, and T is your time in years. So it's really kind of an easier formula than our other ones because it spells out a nice word. So in this formula, Nick invests $500, earning 7.5% interest, compounded continuously. So the first kind of problem is where they give you the T and you just plug in everything into the formula. So Nick, he's investing $500. Since it's compounded continuously, we're using E. The rate is 7.5, so when we make it a decimal, it's 0.075. And T is 5 years. So when we do all this, so we're doing this for n of 5, excuse me. So to the nearest dollar, it says here, is 727.49. So the nearest dollar is $727. So how long would it take for him to triple his investment? Well, his investment was initially $500. So tripling that would be 3 times 500. Hopefully you realize that. So when we write the formula, this is 1500 equals the PERT formula, E to 0.075, but we don't know now is our T. It's not 5 years now, we don't know, so we're going to try to figure that out. Those of you that understand how to use ln, I suggest you go ahead and do this. But I'm going to make this video for those of you that don't get that and just want to use the log. I'm writing astronomically big right now, so I don't know why. I already ran off the page. But anyway, so I'm going to take this, throw it out in front, so it's log of 3 equals 0.075 t times the log of e. Divide by the log of e, and you get like 1.0986 repeats, whatever stuff happening there. And then when we divide by 0.075, we get 14.648 is your T. Now this one, of course, me being me, forgot to actually write what to round to. We're going to do the nearest tenth of a year here, just because it's compounded continuously, so at any point we will have that time. So 14.6 years. Normally they will tell you, it's just me, So compounded continuously is interesting. It's used in finance quite a bit. Half-life is also, and that's used in science, anthropology, in a lot. Okay, a lot of science involved here. So here's an application that you will use in life, or you may use if you go into this field. So let's say you have 500 grams of something, and the half-life is, just to make it easy, 1 year. That's your half-life. So how long would it, let's say after 5 years, how much are you going to have left? So after 1 year, you're going to have 250 grams of that. So every half-life, the whole thing gets reduced by a half. That's why we call it half-life. So after the second year, we're going to get 125 grams. After the third year, 62.5, and so on. So this formula up here, the time is on top. So in this case, let's say it's 3 years, and the half-life is on the bottom, which is 1 year. So it's always time, like how many total time you have, divided by the half-life. Just make sure that they are in the same units. Because you can't have, like, you couldn't do like 6 months as your half-life and 5 years. Okay? You would have to convert this to either months or this to years. So just make sure that they are the same unit. So I don't know why I'm erasing it, but it's very satisfying. Okay, so carbon-14 is one of those very common things that you've heard of before, I hope. A lot of anthropologists and that thing like to date artifacts using carbon-14. Really, really old ones, because a half-life is actually 5,720 years. So unless something is older than 5,720 years, this really isn't all that useful. So really old things. So let's say Dr. Frankenstein, let's make up a formula for his 300 grams of carbon-14. How much will remain after 1,200 years? So you can figure out things that are less, you're just dealing with less than a half-life. So remember how much time goes on the top and how the half-life goes on the bottom. And then you just, plug it into your calculator and figure out your fancy number. So in this case, it's 259.398 years. And we'll figure this out to the nearest year because I forgot to tell you where to round again. So there's 259 years. Grams. Did I really just write years? Hello and welcome to a snow day. So, grams. Which isn't that much, which makes sense because after 1,200 years, there should be still more than half of it left. After 5,720 years, there would be 150 grams left. So there should be more than that. So then we have the alternative way that we ask this. How will we reduce this to 10 grams? So that's, when will it be 10 grams? How many? We're going to say, no, nearest 100 years. I remembered this time. So we have 300 grams. We have a half-life. We don't know the time, but we do know 5,720 is the half-life. So there's our formula. There's only one thing we don't know, so we need to find it. So we divide by 300. This is our usual way of solving. So this is 0.033 repeating. Remember, don't round, ever. Well, okay, you can round at the end. Log both sides. This thing comes out in front. And we're left with t over 5,700. So we'll divide by the log of 0.5. And it's like 4.9068, etc. Just leave it in your calculator. So to get rid of the 5,720, I'm going to multiply. And we're just going to be left with t over here. This multiplied together, 28,067 years, 0.4-ish, etc. So if I want to round to the nearest 100 years, the number's right here. So it's 28,000. I look here, this is a 6, so this goes up to a 1. 28,100 years approximately. Alrighty, have a good day.